Dear colleagues, we are beginning the panel session for the defense of the thesis by Sergey Kovalev. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 010204, the mechanics of hard body under deformation, and the topic is determination of compressive eye strength under the full-scale conditions by borehole jack. Yes, it's February 16th, 2 p.m., and we start our session. Our members of the board were approved by the order by the Academic Secretary of St. Petersburg State University as of November 30th, 2020. And you know that Petr Yevgenyevich Tovstik was appointed the chairman, but unfortunately he passed away, therefore, under the order issued by the Academic Secretary of St. Petersburg State University as of February 3rd, 2021. I, Svetlana Bauer, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Theoretical and Applied Mechanics of St. Petersburg State University, was appointed the chairperson, and here are the members of our board: Yulia Pronina, Doctor of Sciences, Associate Professor, Professor of the Department of Computational Methods of Deformable Body Mechanics, St. Petersburg State University; Professor Resnina, Professor of the Department of General Mathematics and Informatics; Professor Filipov from the Department of Theoretical and Applied Mechanics, and Professor Ivanova, Professor of the Higher School of Theoretical Mechanics of Peter the Great, St. Petersburg Polytechnic University. The following members of the board are working remotely today: Gennady Mikhailovich, Professor Head of the Department of Bio and Nanomechanics of the Belarusian State University from Belarus. Gennady, do you hear us and see us? Gennady? Yes, I do. And Lydia Nazarenko, Doctor of Sciences in Physics and Mathematics, Senior Researcher at the Otto von Guericke University at Magdeburg, Germany. Lydia, do you see us and hear us? Yes, okay. And we also have our candidate for the degree, Sergey Mikhailovich Kovalev. And we have one thesis supervisor here, working remotely, and the second thesis supervisor. So the first supervisor is Viktor Smirnov, professor and leading researcher of the Arctic and Antarctic Research Institute, and he will work remotely. Today, as I've already mentioned, yes, we're waiting for him to turn his camera on. And the second supervisor, Galina Pavlainen, candidate of Sciences in Physics and Mathematics, Associate Professor of the Department of Theoretical and Applied Mechanics of St. Petersburg State University. She's here in the room. And dear colleagues, in order to improve the quality of our connection, kindly turn off your microphones, but don't forget to turn them on when I give you the floor. And I would also like to inform you that the panel session of our dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted into English. Currently, we have an email address posted on the page with live broadcast of the board session, and all listeners can submit their questions to Mr. Kovalev online, the questions regarding the thesis or the scientific discussion. These questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions must be related to the presentation and to the content of the thesis. And don't forget to give your name and position if you submit a question. And under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the board is valid, providing 2/3 of the appointed board members are present. Our dissertation board consists of 8 people. 7 are with us today, including 2 members of the board remotely. We have a multimedia connection with all the members of the board as well as with our candidate for the degree. Therefore, we have a quorum, and our session should not last more than 2 hours today. And the agenda is as follows. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. 5 minutes for that. The candidate's presentation providing an overview and findings of the research, 15 minutes for that. Questions to the candidate regarding the presentation, 10 minutes per question. Then candidate's replies to the questions, 10 minutes overall. Then reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions and remarks. 10 minutes per speaker. Next comes chairman's. The chairman's report on the thesis, 10 minutes. As well, the candidate's comments about the report on the thesis and replies to the questions, 20 minutes. Then open discussion. Anyone willing to speak out may take the floor and say their positions and ask questions. And I kindly ask everyone willing to speak out to fill out the registry form and introduce him or herself before they're given the floor. Then the chairman will ask questions submitted during the broadcast via our website. If any such questions are submitted, then the candidate will reply to these questions. Then we will give the floor to thesis supervisors, 3 minutes per supervisor, and then 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. And the discussion of the results of the defense is not broadcast. Next comes open balloting, vote counting, and recording of the results in the protocol. Then making a decision on whether to confer the academic degree or not. And finally, the candidate's closing speech, no more than 2 minutes for that. Distinguished colleagues, any questions or comments on our agenda? If there are no questions or objections, let us proceed. And before we do that, I kindly ask you to switch off your the sound on your mobile phones. So, let me start. The thesis by Sergey Kovalev for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 010204 mechanics of hard body under deformation, is titled Determination of Compressive Ice Strength under the full-scale conditions by borehole jack. The thesis was approved for the defense by the order of the academic secretary of St. Petersburg State University, issued November 26, 2020, number 10768/1. Mr. Kovalev has prepared his dissertation based on ARI, and Viktor Smirnov, Doctor of Sciences in Physics and Mathematics, leading research of the Arctic and Antarctic Research Institute, and Galina Pavelanian, Candidate of Sciences, Associate Professor of the Department of Theoretical Science and Applied Mechanics of St. Petersburg State University, are the dissertation supervisors. So the list of 13 published works describe the main research findings, and in peer-reviewed journals recommended by the Ministry of Education and Science, we have 4 publications, and as for papers in publications indexed in Web of Science and Scopus, 4 papers as well. And we also have 2 monographs with co-authors and 3 patents for inventions. The candidate has submitted the full set of documents to the academic secretary, Mr. Gnyotov, and the above-mentioned documents comply with item 12 of section 3 of the order on the procedure of granting academic degrees at St. Petersburg State University. All the documents provided are found in the certification file as far as I am informed, and they are and the copies may be found if you ask the curator of the defense, the member of the dissertation board support department. And before we listen to our candidate for the degree, I like to ask you if there are any general questions, and if I would like to ask if there is a need to consider the full list of documents submitted. No questions. Okay, so Sergey, please, you have the floor. 15 minutes overall, please. Thank you so much, dear colleagues. Hello. The ice cover can seriously destroy engineering structures, and you see an example near St. Petersburg in the Ust-Luga port. we had this range mark, and after the drift it was damaged, and here on this slide you see the consequences of this impact of this ice field. You see that we no longer have range marks, and the structures are deformed. Therefore, in order to avoid such extreme events, we need to know the real strength characteristics of ice. And traditionally, the strength characteristics are defined based on the test of samples cut out from the ice flows or ice formations. And in order to get such samples, we need to organize a lot of works. First of all, we need to drill this block, drill out, to take it out to the surface. And then we should mark the horizons that we're going to use for the tests. Then we mark the specific areas for drilling, then use special equipment. Yes, after that we drill the block, drill the small cores, then treat them on a special installation to provide for the necessary structure, and then we test them. And as a rule, we're interested in ice characteristics at the point when it has its major thickness in springtime. And there is an impact of solar radiation that should be considered here, because the overall temperatures may be quite high. And as soon as we extract the ice block, these negative factors start to add up to the case. And we try to minimize the time from extraction to test. Yet, no matter how hard we try, this time is still rather big, and we test the samples with some changed characteristics. Therefore, we need to develop new non-sample methods when we want to define the ice strength. The goal of my work was to define the strength characteristics during compression in real conditions. And in order to achieve this goal, I had the following problems to consider. To develop, to produce and to test new equipment to define the local strength of ice, to devise methodology in order to define the local strength, to define the characteristics of local strength according to the method developed, then compare the ice strength considering the developed and traditional methods, then define the formulas, devise formulas for the calculation of ice strength depending on the liquid phase content, and they assess the impact of the speed of indented penetration on local strength and assess the anisotropy. In the ARI, since the year 2000, we've been devising methods to define local ice strength using borehole jugs. Since then, this jug was modified quite seriously, and now this complex of borehole jug consists of the following components: hydraulic station that has a flow regulator that allows us to define the speed of indented movement, and it does not change when we have a rise in pressure. So that's the measurement block here as well, and the registry block. Also, we have our jug over here. Then, in order to carry out comparative tests, we have this hydraulic press that works from the very same hydraulic station. As for the jug itself, it is the base plate, hydraulic cylinder with a movable piston. And in the end, you see this indenter. As for the form of this base plate and in the jug, you see they provide this close connection to the side of the well. And here you see the placement of this complex on the surface of the ice flow. Hydraulic station, multiplier, measurement block, and jack. And the complex is operated the following way. On the ice cover, we use this auger motor drill to drill out a well, and over it we install a tripod with a probe, with this jack. It goes down to the well, and in 30 centimeters it takes measurements of the local density. So the hydraulic station increases the pressure in the hydraulic system, and the piston goes out, and it pushes the indenter to the side wall. During the tests, we fix the following parameters: pressure in this hydraulic system, then the movement of the jack, and crack formation processes as well. And these characteristics are registered via the AD plane. The penetration of indenter can be divided into 3 stages. The initial one can be seen on this scheme. You see the change in pressure in time, and we see the formation of the first crack here, and on the second stage we see the destruction of a certain volume of ice. The stress in ice reaches its maximum peak point, and we call it a local strength value, or peak or destruction stress. That is quite a quick process, and after we achieve the maximum stress, it drops, and on the third stage we see the penetration of indenter to this crushing zone at a permanent stress which is lower than the peak one by 20 or 40%. As for the test results of local strength, we draw the vertical distributions of ice strength across the entire thickness of the ice flow. And as for strength characteristics, they are unevenly distributed in the thickness of the ice and on the surface of the ice. And working in real-time conditions, it allows us to assess this heterogeneity. And for example, you see the measurement of local strength on polygon 24 45 meters, and you see 2 areas with increased density and several areas with rather low density. And defining local strength of ice in ridge formations allow us to define the thickness of consolidated layer. And consolidated layer means these are the most the strongest area of the ridge. And over here you see the profile of local strength in the ice ridge, and you see this consolidated layer quite well. I won't dwell upon the physics, characteristics of ice, of the seas in which we had our measurements done. Yet such tests were carried out in the Caspian Sea. This work was used in order to develop local technical conditions, according to which we constructed the oil platforms on Ulyanovskaya and Kachagin oil fields, and today they are extracting oil in the Caspian Sea. And in the north, such measurements were carried out at Baydaratskaya Bay and Anadyr estuary. As for the Baydaratskaya Bay, the works were carried out for the laying of pipelines, and as for Anadyr estuary, we used such works for the design of the port. And in the Far East, we worked in the Novalsky Strait also to lay down the pipeline. And similar works were carried out at the Baranov, at the ice base Cape Baranov, and that is the station where we can organize our scientific studies. Local strength works have been carried out since 2016, and these works were carried on an annual basis at Baranov Cape. And also local strength was measured in the Transantarctica expedition, that's basically the north of the Barents Sea. We used the drifting station of the novel type, and academic Tereshnikov worked with us. That's the research vessel, and such experiments were also carried out during the recent Mosaic expedition. So, this graph gives us the results of measurements of 759 ice strength points, depending on temperature at Baranov Cape. And we also offer a linear dependency of the data that we acquired if we consider the temperature of ice. And we see that we have quite a lot of experimental data collected, and the correlation coefficient is quite high as well. The neighboring graph gives us this first line, the dependency that we got at Cape Baranov, and line 3 gives us the temperature dependency by Johnston, received at the Canadian sector of the Arctic, so it's square, you see, and just for comparison, we also give this square dependency for our measurements as well. And we see that in low temperatures, they are quite close, and as for the differences, we have them when the ice temperature is high, and mostly this can be connected with the fact that in high temperatures of ice may have different destruction stages. On this slide, we see the dependencies of local strength on the liquid phase volume. And as strength characteristics depend on salinity, structure density, and so on, the volume of liquid phase actually unites temperature and ice salinity. And we also have this dependency by Spencer and Morris, and we see that our data demonstrate higher values. Maybe that can be explained by the fact that Spencer and Morrison united all the literature data, not for 1 year ice and our dependencies for 1 year ice, but they also used old ice, 2 year ice, and so on. During the jack penetration, when we have some glacial movements, these fibrous crystals are growing not spontaneously, but they are ordered so that the optic axis will be aimed along the flow. And during the jack penetration process, if we talk about these fibrous layers of ice, we may see certain differences in the destruction during the penetration stage. On this picture, we can see this cut in polarized light, and we see the destruction of ice under the indenter impact, and you see the prevailing direction of crystals. And here we see the perpendicular penetration, and we see that the full destruction zone on this picture So here we had parallel introduction to C-axis, and here we had the penetration that was perpendicular to C-axis. And here we see the horizontal thin section, and we see the consequences of this penetration introduction process, 40 degrees to the main axis, and we see that certain asymmetry in the destruction. And numerically, we see that the impact of this direction of penetration is not that significant. We see two strength maximums when we introduce parallelly or perpendicularly. So local strength is 4% lower, and the minimal strength is achieved when we introduce the jack at an angle of 45 degrees. That's 12 or 13% lower than the maximum ice strength. When we change the speed of jack penetration from 4 millimeters per second to 0.5 millimeter per second, we also observe certain drop of the average local strength. For example, you see the square dependency of the change of local strength depending on the penetration speed. And these tables give us the correlation between the local strength and the strength of samples at single-axis compression in the Russian freezing seas. We see that this correlation is changing from 4 to 5, and the average value was 4.6. This slide gives us the substantiation of the fact that the definition of local strength in case of 9 centimeters diameter, we see that here we have a step of 30 centimeters. And in conclusion, I provide the answers to the questions and the goals that were set in the beginning of the study. We devised a method for the definition of local strength. I developed equipment for such measurements, and this method was also used to define the local strength of ice in the Far East, in the South Seas, in the North Seas of Russia. We provided linear and square dependencies of local strength on temperature of ice, and we also offered the dependency of local strength on the liquid phase volume. We also carried out a study on the anisotropy impact on local strength, and also the changes of local strength were measured when we considered the speed of jack introduction. And we also carried out the comparisons of local strength with the strength of samples in single axis compression, and we demonstrated the differences. And yet another important point that I wanted to mention is that such work is the first, if we talk about the summarization of works on local strength. And after it was performed, it became clearer where to move forward. Now we see some weak points. We see what we need to do later on. We need to study the local strength dependency at high ice temperatures. We need to study the impact of jack diameter on the local strength. We need to carry out the comparison of characteristics obtained for different types of ice depending on the structure. For grainy, for fibrous ice, for intermediary stage, and so on. That's it. Thank you. Yes, I believe I didn't take too much time. Any questions on the report? Yes, I want to ask a question. I wanted to ask you. So you started your report saying, talking about the catastrophic consequences that the ice may have, and if you would measure the local strength of ice in Ust-Luga, how would it help to avoid this destruction? You see, there's a range of such goals there, and we have Viktor Mikhailovich with us today, and he was the member of commission on the investigation of the reasons of this accident. And I believe he would say it better, but the thing is that this range mark was developed according to the GOST standard. Yet it turned out that this ice field drifted from the north. It is more dense. These field characteristics were not considered by GOST standards. So you see you see a stronger ice flow coming there, and it actually pushed this range mark away. And if we had such a goal, we would study not just these ice fields in place, but also the hydrological regime. We would investigate if there is a change, if there's a chance that an ice flow may drift from the north, because you see such conditions can't be predicted. You never know where it comes from and what are the hydrometeorological conditions in place. Therefore, we need to take into account. We need to take everything into account, and it is likely that with given higher strength characteristics for ice, and the customer would say, you're giving such characteristics that the country will have no metal to create these marks according to your requirements. So see the GOST standard, and you see in this case we would have just the same. So if you know this local strength, you would recommend to have denser metal. We don't issue recommendations, but we can say that the ice may be of such and such strength, and we may have certain problems. And what they do next is the problem of designers. And there's technical conditions for oil fields in the Caspian Sea. We also provided the characteristics of ice and the powers that may happen there, and the designers did their part of work after that. Okay, I have yet another question. You mentioned that it's clear that we need to study the indented diameter and other parameters. So do you plan to carry out experiments, or do you have any plans to add up some analytical calculations? So I'd be happy if theoreticians join in, and in due time we planned such works with Professor Shkinik, and Viktor Nikolaevich had several articles published with him together. Right now we have Far East Federal University that joined us, headed by Professor Becker. So such works have already started, and they devised one of the ice strength criteria in which we use this borehole check. But still, that's not enough. Certainly we need more studies, and it was already mentioned that we have one theoretical work by Masterson in the definition of local strength. And there were no other theoretical works published, and we all are focused on this work We're always taking it into account. It's not bad. It works. But according to Masterson theory, this correlation between the local strength and sample strength in a single-axis compression should not exceed 4. And overall, we have 4.6 as a value. But as we compare the single-axis compression, we reduce the density of the samples, because whatever we do, we can't just extract a sample and test it at once, because there is sun that changes the ice characteristics, and we're likely to get a reduced strength. And the same is true for tests and regulatory documents when we carried out the single-axis compression for certain installations. But this is compensated by this additional excess of strength. Any other questions? Yes, please. I have the following question. In some standard packages like ANSI and others, are there any experimental data regarding ice? When they develop packages, do they add up this experimental data? Are these experimental data needed? Well, it's hard to answer the question straight away, because I did not work with this package. But maybe some specialized packages that calculate. Well, you see, I've heard such reports at conferences on models, destruction models for ice samples. And there were many of such models, but what I don't like here is that they try to invent this strength of crystal attachment. But I say that you destroy the sample not because you just break down these ties between the and we need to consider the defects that this sample has. And these defects are not taken into account. So measure the adhesion strength of two crystals. So let's give it a try. Let's add that to the value to the model. And after that, let us consider the inclusions and try to reduce the density of samples. Yes, that's quite a complicated process. It's easier to reduce the adhesion several times and to get a close result. But for samples in other place, you need to select yet another adhesion strength and do the same works all the time. And you need to devise a model for each sample. That's what they are using today. Okay, thank you. Any other questions? None? Okay. Then I'll give the floor to the members of the board. We had no external reviews right now, and now the members can read out their reviews. Maybe not fully because they were already published on the website. Maybe you can give just the major points. And our candidate for the degree can answer the questions at once after each report or after all the positions are voiced. So what do you prefer? Yeah, whatever. So let's answer each question at a time. So all the reviews were already published on the St. Petersburg State University website. So you can read out the major ideas, the major points. So first of all, I would like to give the floor to Professor Mikhailovich. Professor, please. Microphone, please. Yes, thank you. Well, I liked the work. That's an interesting work from the point of view of its application. It is really important, and as for scientific importance, it is in the development of non-sample method in real-time conditions. I believe that's quite an advantage if we compare the current techniques and this device method. And the square dependency of local strength from temperature is also very interesting. That it allows us to calculate local strength for many Cs. And I'd like to dwell upon my remarks. Overall, I have a positive assessment, but my comments are as follows. Two of them are just methodological. I believe you should have defined a local strength better, because there are three stages in Danta, and the destruction happens on the first stage. On the second stage, there is crack formation as well, and maybe you should be based on the diagram. Maybe you should have said that that's maximum peak pressure, but that's methodological issue, you know. Second remark was already mentioned. Did you carry out the impact assessment for the indented diameter and the correlation of diameter to the well diameter? Maybe there is a fixed value here that gives us the true assessment of local strength. It was already mentioned, and it was one of my comments. And third comment was there was a misprint there with ice thickness study. When you measured this ice thickness, I didn't get how you define this HI. You just dropped the indented one parameter of depth, and then how did you define this thickness? You dropped it further. What? During the introduction process, you see the deformation of the entire flow, and how did you define this HE? So these are the questions that I wanted to ask. Yet, regardless of these comments, I liked the work. I believe it complies with the requirements of the Higher Attestation Commission, and it deserves the award of the academic degree of the candidate of sciences in physics and mathematics. So these are the three remarks that I had. Okay, please. Yes, I agree with the fact that I had a rather poor wording of this local strength. Certainly there's a drawback, but for us, you see, it's quite obvious. It's routine, and I just don't... and I just couldn't see that I didn't give this definition because I'm so used to this term. You see, yes, certainly that's a drawback. And in my speech, I tried to consider your words and demonstrate what local strength actually is. So, you know, you just get too used to this, to these terms. And as for this misprint with HI, initially I had H and Cyrillic L. And before I submitted the work for publishing, they said, why do you take Cyrillic alphabet? Because we may have certain replacement by some unclear items. Therefore, I replaced L, Russian L, by ice, and I did not pay attention to the fact that that's a sum index I. So that's a fact that can be explained by this being in a hurry. And as for this correlation between indented diameter and well diameter, that's quite a complicated issue. Why? Because certainly we want to use the higher diameter jack, especially for fibrous ice, because we want to catch as many crystals as we can. And if we use some small sample, we are moving to this density experiments. And we don't want to consider this firmness, we want to consider strength. And as it was already discussed at the international arena for sample tests, the size of the sample should exceed the size of crystals 8 times, and for grained crystals this is not a problem. But when we are working with fibrous crystals, we may face certain problems, and it's good if the size of the crystal is 1.5 or 2 centimeters. We have a 14 diameter, the diameter of 14 centimeters for single axis compression. And what should we do when there are dozens of centimeters of this crystal size? Just full-fledged studies for the entire ice area. And the same is true here. We are trying to find this correct diameter to catch a larger crystal, but if we increase the well diameter, at once we see the rise of weight. And we are very limited in weight, especially if that's a helicopter expedition. The equipment should be compact, rather light. Therefore, we can't get out large samples. So here is this optimal well diameter, 25 centimeters. The equipment has the much needed weight. And as for the jack that we can use, it accounts for 9 centimeters. Certainly we can have a more powerful hydraulic station. Yet there is a question of weight at once, because this increase, we have this 27 megapascals, and if we have a rise here, there is a rise in weight. Therefore, we decided not to use this large dimension hydraulic stations, and we used multiplier. So we lost speed, but won additional weight and capacity. So maybe in these conditions, when we have the diameter of 25 centimeters, maybe here we'll try to select other indented diameters. We have 12, 6.5, and 9. Unfortunately, 12 centimeters does not work quite well on cold ice. We don't have enough power. The indentation is quite large. We don't see this ice destruction in this case. Take a weaker ice and carry out comparison analysis. Here, that's certainly that's the work to be done. And maybe after such experiments, we'll get back to well diameter issue. Not to increase, but rather to simplify the process. We devised a 16 centimeter diameter indenter. So we'll organize such experiments and get back to the issue later. That's it. So, did I forget anything? So, Gennady, are you satisfied? Yes, I wanted to get back to the third question. See, you mentioned a misprint, but I also mentioned this formula 2.5. You had this h small for thickness. Yes, I got it. So, how did you define the thickness? Yes. You see, we carry out experiments with a stop of 30 centimeters in a well. And these margins of layers are just in the middle of these tests. Okay, I got it. Thank you. Okay, is that it? Now I can give the floor to our next speaker, Lydia, please. Well, I had a very good impression because the work has a lot of new results and the description of new experimental equipment that improves the accuracy compared to other instruments, and it really simplifies that technical process of ice measurements. And also the work has descriptions of new methods for the definition of this ice strength, and also the local strength analysis for different seas. So we see that there are new results in this research. The topic is quite a relevant one, and it has practical value for engineering goals like laying down pipelines along the sea bottom and different structures and so on. So overall, formally the work corresponds with all the Higher Attestation Commission requirements for this specialization. I had just a short technical remark, and I've already understood where the problem was in this discussion in this Formula 2.5. The definition of ice thickness is HI, and it looks like some index, but now I understand that that's ice index. And I've already mentioned that this work complies with all the Higher Attestation Commission requirements for this specialization, and I believe that Mr. Kovalev deserves the academic degree of the candidate of sciences in physics and mathematics in this specialization 01, 02, 04. Okay, that's a repetition, so you have no question to answer. Therefore, let's shift to our next review. Please, Yulia, you have the floor. Hello, dear colleagues. I won't repeat all the results. I believe that the relevance, the scientific importance, and the practical importance and novelty, they are quite obvious to anyone, and that's a fair research. That's fair research, and I'm really fascinated by the fact that Sergey, facing quite a practical problem in a world that has very strict frameworks and standards, he outstepped these borders and did not perform just technical work according to these standards, but he rather optimized the work and the process of study at nearly all the tiers. So he devised new technical equipment, he devised new methodology, and using it, he performed all the studies needed and also introduced an offer on the change of the standards. So the work deserves the academic degree, and it meets the requirements of the Higher Attestation Commission, and I fully believe that Mr. Kovalev deserves the academic degree of the candidate of sciences. Yet I had a number of comments, some of them just quite technical, and we already considered these questions with Sergey at a workshop. Therefore, I'll just read some of them. The thesis. It would be wonderful to give an overview of certain studies on mathematical modeling in such a work, of this mathematical modeling of this mechanic ice behavior, and to find out whether it's possible to use this data or not, and also maybe it would be wonderful to compare this work with the works that were already carried out at Krylovsky Scientific Center, Vyshninsky Center, or at other centers as well. So, and also it would be interesting to consider the approximation using the square dependence I mentioned it not just for 3.1 image, but for the previous images as well. This dependency of ice strength, depending on the temperature. Was there a dependence on the square and linear and dependencies? Was it stronger? Was it weaker than in image 3.1? And I won't read out these technical points, but I believe we all should be attentive to such points. And I've also had a comment here that was already taken into account, because Sergey mentioned that when he compared his results of experimental data with foreign scientists, he mentioned that it's important to consider the influence of the type of ice. But overall, this thesis has all the results in one bulk, in bulk. And just for the future, I believe it would be wonderful to organize certain classification of all these dependencies for different types of ice. And after that, find certain correlation. And overall, I believe that that's quite a good work, and I will vote for the award of the academic degree. Okay, thank you very much. When I delivered a report for the first time at our department, I gave certain results of the theoretical works on the drug penetration behavior. The results of Shenik team, and these results were published in joint works with Viktor Smirnov, and I don't remember who was there among the co-authors. So I mentioned these works, but we concluded that we shouldn't do a literature overview in this work. I don't remember whose was this idea. Maybe Galina remembers that. Just to make a practical work without literature overview, so that it won't have. Maybe it was Piotr Evgenievich who mentioned that. Yes, I can explain that this thesis had 3 testing stages. First, the report at the theoretical and applied mechanics department, then the report at the Department of Computational Mechanics Methods of Deformed State, and in Material Resistance Lab. So 3 times we had this testing of results, and Sergey gave us this new information on ice, because before that it's the first thesis that is dedicated to ice strength overall. Yes, there are a lot of such works for wood, for plastic, for metals, whatever you please, but not for ice. And that's a pioneering work here. And Piotr Evgenievich mentioned that the work is such an innovative that Sergey should concentrate on his own results. And as for the previous results, they are well known already. Therefore, Sergey concentrated on his results, because he has been working on ice for the entire professional life. Yes, and he graduated from the elasticity theory department of the Faculty of Mathematics. So that's it. That's my answer to the question why there's no literature overview. Certainly it would be wonderful to have one, because that's a pioneering work. We never read such works before. And Petr Evgenievich said that he could never imagine that it would be so interesting, and at once he gave research works for his students, for 2 of his students. Lighthouse drop That's also a problem that Finnish scientists face, Swedish scientists face. So the students are now working on these problems. We like the topic and we will continue using it later on. So we'll help the ARI and ARI will help us with new experiments. Yes, certainly. Certainly, we are ready. We'll be happy to cooperate. Yes, and they said we need to translate the work into English. Why do you need such a volume? So that's how it happened. And therefore, we decided not to use this literature review. And as for lack of division into types of ice, you see, I don't have it because, first of all, we thought about this geography. For example, we calculated this index in the south. Can we use it in the north or in the far east? First of all, we wanted to find out whether we need to organize such experiments for every measurement point. And now we can see that there is no geographic connection, and there's no temperature, salinity dependence. And as for structure, the structure dependence may be relevant to the type of ice, to the structure of ice. Certainly, this work will be carried out, will be fulfilled. So we'll divide into types. And yet another question, I forgot it, unfortunately. Comparison of linear and square dependency of strength and temperature. Well, we can give a square dependency for local strength for K. Baronov for every year. And that's actually the way that Johnston uses. He provides square dependencies because he has the shift to small strengths. So giving a square dependency, it's not a problem, but it seemed to me that we need to try a different approach, because square dependency, you see, we start thinking if the temperature will be lower, we'll reach maximum, and during the continuous drop, our strength should drop as well. So we need to consider the temperature anyway. And I believe we should separately analyze the local ice density at high temperatures, because high ice temperature can be observed in at different destruction stages. For example, we may have high temperatures at the bottom when there are no crushing processes, and in summertime when we see the destruction process. And they start not at melting temperature, because we see the impact of solar radiation when the ice is still cold. We see this radiation heating sources, and this leads to a rise in porosity. And for such local strength at the destruction phase, we should have a dependency on porosity rather than on temperature. And here, I believe we'll just get out this low local density at this porosity level. And as for the ice that had no destruction stages, we'll use linear dependencies there. Well, I'm not sure about lower temperatures yet. I believe that we can just guess here. minus 30. Well, we worked at minus 30, and our equipment does not withstand such temperatures. People would, but equipment not. So I'm satisfied with the answer, but if you're going to work with porosity, porosity does not give us all the answers, because you need to measure the pores as well. There's not enough to use just porosity here. Yes, the question, yes, but not right now, I believe, yes. Well, we can use Wick's formula for ice. We need to take density and salinity and temperature, and that is the ice under destruction. Yes, we may measure temperature, salinity, and density. As soon as we get out a sample, we see the brine pouring down, and sometimes it just goes in streaks. And as for salinity, well, we can take salinity. As for density, this sample will... Was it your comment on the measurement of density using photos? Well, this sample will be even worse. What are the size of this sample? How can we measure its size when it's broken down already? And we can weight, for example, ice in liquid and on air. But in this case, all our pores will be just taken out, and we get a rather high density. So it's hard to calculate this porosity. So that's a question. Yes, I know. As you've already mentioned, so it won't resolve all the questions. So try to calculate this porosity, and it won't give you all the answers. Okay, let's give the floor to Natalia Resnina. Dear colleagues, so first of all, Sergey, thank you very much for this interesting work, and I support this work for two reasons. First of all, I work with experiments, and it's really nice when you see experimental works in mechanics of hard body under deformation. And the second point is that experimental scientists know that the value of results of in situ experiments is incomparable with the numerous results that you get working not in direct research, and that's true for all things, including ice strength. So comparing, that's one thing when you use an indenter at a huge ice flow that has structure, that has size, that has porosity, salinity, and so on. And there's another case when you take out a sample of this flow taken from some local area, and in such standard experiments, and that's a more local strength rather than the strength that you measure in situ, because you're working on a large slab. And certainly, as for the value of this work, it's not questioned at all, because you see, we see this lack of experimental data that does not allow us to develop good experimental models to describe the existing processes adequately. Therefore, based on your data, those who are going to create these models, they can use this data, they can carry out approximation and testing and comparison with experimental data. I have a few remarks. Two of them are just technical. I won't give it. It coincides with Yulia's comment. I believe the main drawback of this work is lack of literature review, because one thing are people who work with ice and know these works of other authors, and yet another case when we are unfamiliar with the topic, we never worked with ice, and it's very hard to imagine what others do, how do they do that, and how this work compares with the results of other works. And there was this comparison with other authors as well. And maybe the works you're referring to, I believe you should have described them in the literature review. This would add up value to this work. Second remark, no need to answer that. I understood the reasons already. It is connected with measurement accuracy in the tables. you give local strength with an accuracy of 100th, and the gap is in megapascals or single units. So sometimes the deviation is 4 megapascals. Maybe you could just draw 12 for all the measurements when you had 12.33 megapascals. And the last point is that you demonstrate the dependency of local strength from the penetration speed. And it's really a hard problem, I agree with that, but it would be interesting to listen to your understanding of the physical mechanisms. What are the physical mechanisms of the dependency of local strength from this indenter penetration speed? Overall, the work is a wonderful one. I liked it a lot. Certainly it satisfies, or it meets all the requirements of St. Petersburg State University and Higher Attestation Commission, and certainly I believe that Mr. Kovalev deserves the academic degree. Thank you. I agree that using 100th or 1000th degrees, certainly we may give these results. Maybe that's a bit too much. Indeed, I should use just decimals. You see, this difference is quite obvious. Maybe I should have grouped them in types. Maybe in this case the scatter will be quite significant, and I'll use this. I would need these decimals. And yet another point. That's quite a hard question. I believe that the dependency of this change regarding the speed of indenter penetration, it requires specification. That's just the start. These are just initial experiments that were carried out. You see, I would like to add up theory to all questions, not just to the impact of indenter penetration speed. We'll give it a try, but you see, we don't have enough capacity for that. We have a lab, and local strength is not just the basic field of our work. Then just a small break in this huge wall that the lab is working with. We're now working with a forecast of hazardous ice conditions, ridging, crack formation in the ice flows. The issue is comparable to to forecasting earthquakes. So these are the tasks of similar complexity, and if seismographers have stable bases, our seismic stations are movable and they move, and we move it and we try to make forecasts, yet our processes are much quicker. Therefore, these regularities are easier to assess. And certainly hazardous ice conditions, I don't even compare them with earthquakes. Certainly it's not the case yet. The speed of the processes are different, though there are certain similarities. So unfortunately, yes, that's not our major field, the major field of our lab. Therefore, we don't have capacity for measuring the point. Okay, Sergey, please. Sergey, the microphone. First of all, I was impressed by the scope of work carried out, starting with the development of equipment, and it really is better than similar foreign equipment. And also the results from works in several seas, developing some regularities in these experimental results. And this work certainly was not done in vain. That's quite obvious, because this data can be used in the construction or when we talk about the Arctic shelf. And as for my remark, the first one is the same that Gennady mentioned, the dependence of physical state of ice. When we use different indenters, but there's no data on the dependence of local ice strength from jack diameter. But Sergey has already answered this point. As for two other points, they are just technical or editorial, as some say. You describe the jack, foreign jack, in detail, but you don't give the same detailed description of the jack that our installation uses. It was already described in the report, and it's clear that some things seem quite obvious to Sergey, but people who don't work with this field find it quite hard to understand at once, because I didn't know what consolidated layer is. Yes, and types of ice: A1, A2, B1, B2. I did not sort it out completely what congelation growth is. Certainly in such a work it would be wonderful to give these terms. And as for Sergey, I believe he deserves the academic degree, and certainly his research meets all the requirements of our university. Thank you. Yes, I tried to take your remarks into account in my report. As for congelation, ice formation, that's the formation of ice from liquid water. And how else can it form? For example, phrasal, sugar, infiltration, ice formation from snow. For example, all the glaciers, they are formed from snow. There was no water. Phrasal formation, when ice crystals are formed inside the water, then they rise up and they become the ice cover from the crystals. As for sugar formation, that's snow start to freeze in water, thus forming snow crystals. And as for infiltration, that snow cover, when water goes on the surface, it freezes and ice forms not from this water directly, and there may be combinations, congelation and phrasal and sugar, and so on. And as for these types of ice, A, B, and V, and G, that's the classification of Professor Cherepanov, the best-known Soviet and Russian ice scientist, ice technician. He offered this classification: 4 types: A, freshwater; B, freshened; V, sea; and G, old. A, freshwater ice, that is formed from water with salinity from 0 to 2 promille. B, freshened from from the salinity from 2 to 24.7 per milli, and marine with a salinity over 24.7 per milli and higher. First letter and figure. So we can see that 1 is the largest fibers and 9 is the grainy crystals. So that's the division. I believe you may ask why 24.7 per milli. And here the ice will be completely different depending on the point, because density of fresh water, maximum density at the temperature of 4 degrees, this freezing temperature is 0, and we start to add salt to this water, and when the salinity rises, the freezing temperature drops, as well as the temperature of maximum density, and the temperature of the reduction of strength, it drops 2 times faster than the freezing point, and at 10 degrees centigrade the freezing temperature at 10 degrees will be minus 0.5 degrees, and the density will drop by a degree. So you see, at 24.7 per milli, the freezing temperature will coincide the maximum density temperature. And what do we have here? Freshwater ice, freshened ice, up until 24.7 per milli. The water freezes, it is at the freezing temperature, but it can't drop because we have a bit warmer water at the bottom. It has a high density and it does not allow this ice cover to drop. And when we overcome this 24.7 per milli, that's the marine water that is freezing and it drops, and water comes up, and we see this convection mixture, and as a result the marine water has no bottom line. This so-called bead, these crystals of ice that we see in the bottom. And this leads to a lot of problems, because remotely we still can't define the thickness of the marine ice. We can't get the reflection from this from this bottom. We get loads of different reflections. Different layers may reflect whatever. The signal is unclear, and there is hope that 7-channel probes will be able to define the thickness of marine ice. And Nizhny Novgorod University, they are working using the acoustic method, but right now no one has such an instrument to define this thickness in marine sea. And Professor Cherepanov offered this classification. He worked at our institute. Unfortunately, he passed away. I knew him quite well, and Cherepanov classification, well, that's something on default. Ice experts always use it. No one is saying anything about it. Everything is clear to anyone. That's ingrained already. Therefore, I never thought that I should have explained that. Thank you very much for the explanation. I believe that if you'd given it in your work, this work would increase 2 times in volume. Yes, and as for our probes and foreign probes, I believe that our jacks are much better than the Western ones. And in 2012 or 2013, there were negotiations between the Canadians and our part. They wanted to buy up our jack, but unfortunately there was a sanction period, not from our side, but from Canada, and Canadians banned this purchase of borehole jack. I don't know who won here, who missed the point. I'm not a supporter of sanctions in science yet. You see, they banned it. And certainly the Gidrosistema company did not get offended because they didn't lose too much money on that. They have quite a good turnover already. Yelena, please. Well, I believe I'll be quite short because my colleagues have already mentioned a lot. What I liked most, what impressed me most is that that's an independent development of a technology and independent development of equipment. Second point is the incredible scope of research. And the third point that I wanted to mention is that this experimental work is of particular interest to theoreticians. Therefore, I believe it should be published as a book, or maybe a monography, or maybe an academic book, so that it would be clear to students. Because it seems to me that we should involve theoreticians to the topic, so that not just people who are acquainted with the topic, but it would be wonderful if people from other spheres would have a chance to read this book and to understand that those who are working with the dynamics and deformation of hard body and the static of hard body, because I believe that they would be fascinated as well. Maybe they could organize their own theoretical studies using your results. So that's my wish, to publish this work and make it accessible for broad strata of readers, and also to explain the terms, because there were a lot of questions here as well. Well, maybe to add up a bit of theory to the results. As for the remarks, as I've already mentioned in my review, these are not just remarks, but rather questions that I had when I read the work. The thing is that I had no chance to listen to the report, to the previous reports. Therefore, this interest that I had when I read the thesis so was reflected in these questions. And so what do I have here? On page 29 you write that yet another important factor was the the insignificant development of secondary porosity in ice due to radiation heating. So I had a question: what's the difference between secondary porosity and initial porosity, and how can you define whether the porosity is secondary or initial one? Second question, on page 23 you write the ice texture is characterized by the development of flow beds through the entire thickness of this level ice, and how does this process take place, and what are the factors that influence it? On page 36 you write, as the radiation heating of ice happened as a result of absorption of solar radiation by the liquid phase, the layers with a higher liquid content were heated quicker, and in turn that led to an increase of its volume in layers and to intensification of migration to lower layers of the ice cover. The question is, what's the connection between the heating of the liquid phase from the depth where it is located, and what are the parameters that define the migration speed? On page 48 you write, the rapid ice development and 4-kilometer ice hole created the conditions for the formation of layered ice. Why the presence of ice hole leads to this layered character of ice? Is it connected with flows, water flows in the ice hole, with evaporation from the surface, or what? What's the difference of ice formation near the ice hole or when we have none? Next question, on page 51 you write, the formation of this layer took place up until the full covering of the water area, and after that the subglacial layer was formed, and we saw the rise of formation of fibrous crystals. So the question is, what is this subglacial layer, and how does it influence the growth of fibrous crystals, and how is this ice formed before we see the formation of this kind of action mixture? So, and you've already answered this question. And on page 70 you write, first of all you see the formation of 3 zones of deformed and crushed ice, or the crush zone, the radial crack zone, and the elastic behavior zone. It seems obvious that the size of these zones should depend on the size and the form of the jack. How did you choose the jack, and did you carry out experiments with the use of different jacks? And you've answered this question as well. And the last question, on page 75 you write, using different literature sources we can say that local strength exceeds the sample strength when we have a single axis compression, and the difference is in 2 or 5 times. The question is, what is this start of crushing at the real experiments, and can you easily fix this start of crushing process? Maybe the crushing can be fixed when there is this rather huge deformity or small deformities. Maybe they are not mentioned. So these are my comments. Well, once again, these are rather questions than comments. These are questions, and I like the work a lot. It really meets all the requirements, and sure enough I will support it. Thank you very much. I made up an answer, and I believe my answer takes 5 pages, and I believe I sent it. Yes, Natalia, I've sent you the answers to these comments. No, I've just but the members of the board are not familiar with my answers, are they? Oh, I was sure that I provided the answers already in the written form. I didn't know this. Okay. So if I forget anything, please remind me. So, initial porosity. Initial porosity is the porosity that's being formed during the ice formation. So it was initial porosity. What happens after that? These are some secondary processes, and it becomes secondary porosity. And secondary porosity may also emerge in the pores, in cracks. For example, a crack formed in the ice, and there were certain inclusions that led to this porosity development. And mostly we are interested in secondary porosity. For example, these ice bubbles or salt drops, brine drops that we had in the ice, they start to migrate across the intercrystal layers, and such phenomena give us this secondary porosity, and they are visually different. You see these traces, you see these inclusions, these accurate inclusions that were formed in during the freezing, and if there are certain transformations, you just see it with the naked eye. Well, as for salt inclusions, you know, they are just going between the crystals. And as for the presence of the ice hole on ice formation, you can feel it for several kilometers. How does it influence? And why do we have this layered ice? For example, we have a huge ice hole. And there are a lot of flows here. And for example, there's a lot of snow during the snowstorm, and snowflakes become small crystals, and they are moving under the ice surface. And as we may have a lot of snow during the snowstorm, this flow may take these crystals for several kilometers. They float, get attached to this lower bottom of ice cover, and they make up the layer of grained ice, and they may reach several centimeters. Yes, up until several kilometers, 4 kilometers at Baranov Cape. The closer to the ice hole, the higher the impact, and vice versa. Oh, I forgot other questions. Oh, how this how this flow beds form. For example, we have a salt inclusion in the ice. And as a result of certain processes, for example, there's spring, and we see solar radiation and solar heat reached this inclusion. Each of these salt inclusion, this brine drop, so such drops absorb solar radiation better than the surrounding environment. So this drop absorbed heat, its temperature rose, and it became not a drop, but rather a small line, a small stick. And then they start moving and colliding, absorbing each other. 1, 2, 3 inclusions merged, and they form a small channel. First, these channels, salty channels, are formed. They migrate, they merge, and they form these channels. And when these channels merge, we see this flow bed that may go from the top to bottom, and this brine may flow down, and the marine water will rise up. So that's how these salt channels are formed. Thank you so much. Yes, and yes, I beg your pardon. I wanted to mention that certainly you say that my work, but you know, it's incredible to carry out so much studies independently. So there is the result of my lab as well, ice physics lab, and also we should have 3 people working on with the jack, so you can't generate these results independently. So that is the work of our entire team. And as for my contribution, I've already gave a report on that. But certainly that's not my achievement, my only achievement, because that's our group work, and certainly that's their achievement. That's their achievement as well. I just summarize. Okay, and analyze. Okay, but I need to add a few words and give my review that was already published. I also liked the work a lot. I listened to it twice on the workshop that Yulia organized and we organized, and certain drawbacks that I've mentioned, they also connected with the language barrier that inevitably emerges when we have this neighboring field. And I also wrote, Sergey, he sent me the work of Professor Cherepanov, and I read about this classification. So basically, and today he answered these questions as well. And I had questions on one of the images, on image 3.6, but Sergey answered my question already. Therefore, I have nothing to mention. I'm fully satisfied with the work. Let's decide if anyone has additional questions. If there are no questions, let's move forward. We need to listen to the thesis supervisors. So, Victor, do you have a camera? Yes. Okay, wonderful. Certainly. So, Victor, please, you have the floor. Thank you very much. I had a very good impression from this discussion. And I would like to mention the questions on the report. That's really a good atmosphere, I believe. And if we're going to have such an atmosphere in our country, in such conditions, I believe that's wonderful. I liked the report on the thesis. I've heard it several times. But the questions he got, led me to the point when I want to specify this concept that we have in AARI, in the eye studies. Because what Sergey gave, these are the results of our long-term work on the development of shelf formations. As for the construction, as for the engineering points, as for pipeline laying, these are the main goals, one of the key goals. If we talk about application, so we provide calculations for eyes, for designers, to designers. That want to get very reliable data so that there won't be any accidents. And there were a lot of cases of accidents in the Arctic. Therefore, our works on ice were accumulated by Sergey in such a scope. These are many years of expeditions to the Antarctic, to the northern seas, to drift ice, to landfast ice. And the fact that some of the terms are not clear, that's our problem, because we can't provide definitions. But we have a lot of publications and methodical works as well. if we have a look at foreign works, these questions connected with local strength, that's borehole strength, check. They have other terms as well. For example, large-scale strength on large experiments. And this strength range, this scale effect, that is the fundamental science on the mechanics of a deformed body. And that's what happens in the ice, because we see a lot of the concentration of these problems if we talk about ice. And therefore Sergey delivered a report on our overall results. And these experiments helped him to give this range of ice strength and use these models in micro and in macro scale. And macro and micro scale are of particular importance today if we talk about climate issues, if we talk about the experiments in the Arctic Ocean, on the Arctic Pole. They have this goal of defining the strength. So we should define how these initial cracks form, how they spread, what is the spread speed, what are the effects that emerge. And that's so fascinating, and that idea unites all these goals from theoretical ones to practical ones. That's what our lab is working with. And Sergey is one of the pioneers who joined this academic science, as I see a lot of professors sitting there, a lot of questions. Certainly, these questions will help us in the future. And I hope that Sergey will get back to the topic and will finally defend a doctoral thesis. Okay, Galina, you have the floor. I wanted to explain this lack of literature review. The major studies on the impact of ice on various structures, they are concentrated on the topic, the impact of ice on ports, on berths, on floating atomic stations. And there are a lot of works, thesis works on the topic. And quite recently we had a defense of Mr. Politko, the advancement of ice on the drilling installation, on the drilling rig. And he carried out the calculations using final element method. So he constructed a basic model, how this ice will pass through, how it will be colored, and how this will happen. And sure enough, these works have this practical value and they are quite relevant. But that's the achievement of Sergey, that he made this one step in advance. He does not consider ice approaching the construction and pressing the construction. He assesses its local strength and assesses the potential threat. How many gigapascals we may finally have. And this demonstrates that there is not full calculation that may lead to some mistakes in construction solutions. And if we talk about the forthcoming 5 years, as Gelfand said, that we're going to face very harsh winters, according to Gizmeteo. Considering that, we see that this work is quite relevant. One of the lighthouses that was built in Finland, we believe that it will face the maximum pressure during the advancement of ice from the land. That will be just 5 or 6 gigapascals, and in fact it had 10. So it's clear that this lighthouse dropped and collapsed. So there are no questions from the point of view of relevance, and I was very pleased to work with Sergey, because sometimes our positions of candidate for the degree and thesis supervisor were, so we exchanged these positions sometimes. And because I'm quite a novice in working with ice, yet we should take into account that we will use this layered mesh, because one mesh will be used for ice crystals, another mesh will be used for inclusions, and third mesh will be used for porosity that will be formed. So these are the goals that we are already discussing of working with micro inclusions. And certainly if we add up the computational abilities, we may just make a breakthrough in ice studies. And for me it was quite a discovery to see this plastic deformity of ice, because I was working with metals all the time, and I could never imagine that the plastic ice movement is a fact. Therefore, I would like to thank Sergey for this collective work, for this joint work. I would like to thank Viktor Mikhailovich for consultations and for supervision. And I would like to thank the members of the board for the time. Yes. So it was very interesting to work with Sergey. That's what I wanted to mention. And I hope that he will continue his studies. So, distinguished colleagues, is anyone willing to discuss the work, to say something? Okay, no one? Then we shift to the balloting. So the question is that we can organize a short discussion, closed discussion, but I believe we voiced our opinions openly, and we don't need this break in broadcasting. So, I raise a question on the award of the academic degree of the candidate of sciences in physics and mathematics to Sergey Kovalev, specialization 010204. So we are going to have an open balloting right now. This decision of the dissertation board is on conferring the academic degree is valid, provided more than half of the board members voted in favor. So, as I've already mentioned, we should voice our positions once again. So, Gennady, I support this study. It's quite a good study. I had some more questions, but I'll ask them later on the use of the results of the influence of anisotropy on local strength, and the use of these results for the generation of icebreaker paths. I believe that these are quite wonderful results and important results, and so I just had this interesting idea. Yes, okay, Gennady, so you support the award of the academic degree? Yes, yes, certainly. I do. Lydia, what about you, Professor Nazarenko? I also support this work, and certainly there are a lot of interesting points to discuss, a lot of nuances. So it was very interesting to listen to the report, to read the thesis. This thesis is quite relevant. Certainly I support the work. Professor Pronina, certainly I support the work as well. Professor Resnina, I also vote for. Professor Filipov, I vote for as well. Professor Ivanova, I vote for. So I also support this work. And thus, distinguished colleagues, we had 7 votes and 7 members of the board voted for the award of the academic degree, and therefore the decision of the award of the academic degree is being made. So we award the academic degree of Candidate of Sciences in Physics and Mathematics and Specialization Mechanics of Hard Body Under Deformation to Mr. Kovalev. And as we had a remote session, if the members of the board or Mr. Kovalev have any comments on the procedure, you can say straight away, voice them straight away. And I believe everything was quite okay, and we can congratulate our candidate of sciences. And a few words. Thank you very much. I would like to express my gratitude to my colleagues, to those who work at the ice physics lab, who made a lot of efforts to make this happen, who did a lot. And I would like to thank my colleagues for this valuable experience, my colleagues from AARI, well-known polar scientists. Some are no longer with us today. I would like to thank my professors, the professors of the Faculty of Mathematics and Mechanics of St. Petersburg State University, who trained me, and therefore I decided to join this experiment after graduation. I would like to thank my thesis supervisors, and also to Viktor Smirnov, who guided me in my works in physics lab in 2001 or 2002. I don't remember. Yes, I forgot. I forgot as well. So yes, this was long ago, maybe 2 decades ago. And for these 2 decades, Victor remained a teacher for me. And I would like to thank Galina, because I remember her when I was a student. She was a PhD student then, and she gave us lectures. And yes, I remember her lectures on plates and shells. So I would like to also thank the members of the board for the time that they spent on getting acquainted with my works, and for the remarks that they given, because the majority of these remarks, they are really valuable. And you know, such an overview from professionals it's very important because it opens up new questions. It gives new questions and it pushed me to all the answers. So thank you very much for your remarks. I'll take them into account in my future work, and I really hope that I will continue working on the issue. Thank you. So that is it. Distinguished colleagues, we congratulate Mr. Kovalev. And I close our session. Yes, and we turn off the broadcast.